Welcome back everyone to our second lecture of the series of Basics of Organic Chemistry. We will continue from our previous lecture where we stopped at the discussion at SN1 and SN2, which are the different types of nucleophilic substitution reaction, and now we will be focusing on SNI and SNNGP. So let us start with the description of the SNI reaction, where it is nothing but nucleophilic substitution reaction internal, where some nucleophilic substitution is occurring internally within the molecule, which we'll be seeing later. It is different from both of SN1 as well as 2. How? Because firstly, in case of SN1, we see 100% racemic mixture formation, that is 50% of retention and 50% inversion. In case of SN2, we mainly see 100% inversion, but in this case of SNI, we see retention, there is 100% retention. So nucleophilic substitutions sometimes forms rearranged products. However, when sulfur or phosphorus halides are used, no rearrangement or no different configured compounds or products are formed. And this is a characteristic of the SNI reaction mechanism, where a part of the leaving group will attack the substrate and then detach itself from the rest of the leaving group. So until and unless we see the reaction, we will not understand what is the mechanism. Let us see an example where we have the starting material, and with the help of SOCl2, we will get this product where the OH is getting replaced by chlorine and chlorine atom, and here we can see that the conformation is retained. There is no change in the conformation. So what is happening? Let us see. The first step, R being any group, we have the ROH. The lone pair of this oxygen will attack the electrophilic center of the SOCl2, which is an important part, which plays an important role in this SNI. So this SOCl2, after getting attacked by the lone pair of the oxygen, we can see it will form an intermediate like this. However, oxygen being having the negative charge is highly unstable. So the negative charge will again come back, and chlorine being a very good leaving group, it will leave. This chlorine then will react and take up the hydrogen which is attached with the oxygen, and ultimately it will lead to the formation of an alkyl chlorosulfide intermediate. And this part can be said as a similar to SN1 reaction, where it is attacking, forming carbocation or a cation formation, and then we have the removal of the group. Now second step here is nothing where but when there's dissociation of the alkyl group from the anion. So we have R plus and Cl SO2 minus. So here we can see the actual internal attack, and the dissociation of this bond of R and O is actually favored because of this reaction where chlorine, this is being having lone pair of electron, will attack the positive center of the carbon, and this will lead to the breaking of this R and O, that is the CO bond, uh, as a result of which we will get RCl as our product and SO2 as the byproduct. So try to understand what is actually happening, where first step we have the ROH and the SOCl2, where we will see some attack by the sulfur, by the oxygen on the electrophilic, uh, on the positive centers, and there will be some arrangement of electrons, and ultimately there will be removal of the hydrogen of the ROH, and it will be replaced with the help of SOCl. So we will get an alkyl chlorosulfide. This alkyl chlorosulfide, after that, it will dissociate into two, that is the CO bonds will break. But how it is breaking, it is shown here in the step 3, where when the chlorine is attacking the carbon, that is the positive center, then only the RO bond will break, and this will result in the retention of the configuration giving SO2. Now, sometimes we might need to get an inverted product. In that case, we can use pyridine. Pyridine is an example of solvent which, when used, we will get an inversion of the configuration, as we can see here. We will get an enantiomer. Let us see the mechanism of how pyridine is responsible for forming an inverted product. The first part is similar, where we have the ROH and oxygen is attacking the sulfur, and there is displacement of the pi bond. It forms this being unstable again, the O minus comes to form the pi bond and chlorine is removed. Next we have now the pyridine is coming into action. Earlier this chlorine used to take away the hydrogen to form HCl, but here pyridine is taking the hydrogen to form ROSO2Cl and a cation. Coming to step 2, what is happening here? Again, another molecule of pyridine is attacking the sulfur. The nitrogen lone pair is attacking the sulfur, and the chlorine is getting removed. And here we are seeing the formation of this compound, that is ROSO2N plus C5H5. This, the pyridine is getting attached to sulfur. Now what happens, since the attack of the chlorine from front side is not available, chlorine now will attack from this back side, as a result of which the oxygen RO bond or a CO bond will get cleaved. Ultimately, there will be formation of an inverted compound. This is the main difference. Earlier we could see that since R plus was forming, and because of the formation of this R plus, it was easy for the chlorine atom to directly attack in the front side. But now, because there is steric hindrance, the chlorine has to attack from the back side, resulting in the formation of inverted compound having the pyridine as byproduct along with SO2. So this is the main difference and the mechanism of how SNI reaction occurs. Now, when we describe the rate law, it is almost similar, but the main difference is it depends on A, that is the ROH, that is the substrate, and B, that is SOCl2. This is very important because this is only the reactant, and thus we can see this having a second order. Now coming to SNNGP. NGP stands for neighboring group participation. In case of NGP, we can see that there is direct interaction of the reaction center with lone pair of electrons of an atom, or with electrons of a sigma or pi bond present in the parent molecule but not conjugated with the reaction center. In other words, if we have, suppose, a compound, a molecule, there will be one leaving group, say X, and there will be one neighboring group, that is Y. This Y will just aid or help in the formation of the intermediate, and thus it will help in formation of the stable product which will follow this SNNGP. And here the role of this neighboring group is very important. The nucleophile and the leaving group, these must be anti to each other in 1 and 2 positions, and as we can see in the next slide, we will see how the reaction is happening. So here Z is the neighboring group, and we can see that it is in 1 and 2 position. Neighboring group itself is the nucleophile which will attack this carbon atom having the leaving group, as a result of which an intermediate will form where Z will be bonded with 2 carbon atoms, and X minus will, that is a leaving group, will be removed. Then we have a nucleophile of our choice, it is the Y, which will attack this carbon, and again we can get the compound. Now, with an example, if I want to explain, here we have benzene ring. Benzene has pi electrons, and pi electrons can take part into formation of the intermediate. So when the pi electrons acting as nucleophile attacks this carbon, we will get a intermediate. Now we have NaOH as the base, it is O minus is the electrophile. It is the nucleophile. So O minus will attack this carbon. If it is attacking this carbon, for the breakage of this bond will give us this compound, that is CH2 CH2OH. If OH minus is attacking this side, this bond will break and we will get CH2 CH2OH. So aromatic system acts as neighboring group, and we can get two type of conformations. Examples of neighboring groups, that is any carbon, oxygen, nitrogen or sulfur containing functional groups that have lone pair of electrons, so or negative charge, that is halides, they have lone pair of electron. NH2s, NHR and NR2 all have lone pair of electrons. Oxygens have lone pair of electrons. CO minus, C double bond OR, it has pi electrons. Sulfur, SH, SR all have lone pairs of electrons which can take part in the intermediate formation. Aromatic systems have pi electrons, so they also display the NJP reaction. What are the consequences of NJP? That is, what will happen if NJP is occurring? So let us see some of the results of NJP. First, we can talk about anchimeric assistance. Next, we have retention of configuration, and the third is kind of a sign substitution. So let us see what is anchimeric assistance. So anchimeric assistance means the rate of the reaction is greater than what is expected. We have two examples, hexyl chloride and mustard gas. Both are undergoing substitution reactions with OH minus, and here we are getting this product, here we are getting this product. But when we see the kinetics, the rate of the second reaction is 700 times greater than that of the first. So why is that? Because sulfur having this lone pair of electrons, these take part in the NJP formation. As a result of which, if we consider it as 1 and 2 position, it will attack this position and it will form the intermediate. The chloride will be removed, the OH minus will attack this position, and we will get the compound. So the rate is very fast as compared to a normal SN1 or SN2 reaction. There was a second point where we saw that there was retention of the configuration, which is very obvious when we will be seeing the previous examples. So directly I'm coming to sign substitution. Sign substitution is like when the attack is occurring in a different carbon as compared to the expected carbon. Like for example, in this case, we have the leaving group bromine here. So when bromine is getting removed, and there will be stabilization of the charge by this oxygen lone pair to form this intermediate. Now the attack was supposed to be in this carbon because the bromine was attached there, but because of the stabilization of the charge, now oxygen will attack this in this carbon, as a result of which we are getting a rearranged product as compared to the expected product. If there was no oxygen here, then the OH would have been attacked here only. So this is a result of the neighboring group, that is the participation of this oxygen lone pair. So this is another consequence of NJP. So let us discuss some questions. First is identify which of the compound may give NJP reaction. Now, how can we identify whether NJP reaction is favorable or not if there are any external, like extra source of electrons, whether it be lone pair, whether it be pi electrons in the particular compound? As we can see here, there is a sulfur which is having lone pair. So there is a possibility it will give NJP reaction. Second, here again we have oxygen. Oxygen again has lone pairs, so they can contribute to the neighboring group formation reaction. Next, we have a benzene ring. Benzene ring having pi electrons. We already saw this problem, how an intermediate is forming and how the chlorine is getting removed. So we have seen this already. So this is another example where it will give NGP reaction. Here there is no source of any electron, be it lone pair, be it any pi electrons. So it will not give NGP reaction. Next, we have the question of reaction of alcohol with SOCl2 in presence of pyridine occurs via dash of configuration. I've already shown you the mechanism, how it is occurring. So there will be inversion, as in the normal case we see retention, but because there is pyridine, uh, the reaction of the particular substrate with pyridine will cause blockage in the forward reaction or on the forward attack by the chlorine. So the chlorine will attack from the backward, thus causing inversion. Next, predict the structure with stereochemistry. This OTS is tosyl group. So tosyl group itself has a benzene ring and it is having sulfur. So like, since it is having this benzene ring, this is having the benzene ring. Here it can participate in a neighboring group participation reaction. So this we have S double bond O, S double bond O, and a chlorine is there, which usually gets replaced by any alkyl group, be it R, and we have a methyl group of CH3. This is the tosyl group. So when there will be attack, the nucleophile and the electrophile, it will dissociate and it will attack. Ultimately this OTS will be just replaced by OAC and the configuration will be in the same, like the dashed configuration will remain as it is and the wedge configuration will remain as it is. So there will be retention of configuration because it's an NJP reaction. So this is for now. In my next class, I'll mainly discuss about elimination reaction, the different types of elimination reaction, and I'll show some examples also. So thank you and keep learning.